So welcome back. This is the second video about the Bayesian networks. So we're going to continue discussing Bayesian networks and looking at the idea of independencies. We saw in the previous video that the network structure, it dictates a series of independence assumptions that we call the Markovian assumptions. And we'll further develop this idea. But before discussing this, let's make a few definitions about Bayesian networks. And the first definition is what is a Bayesian network by itself. So we will define the Bayesian network for a set of variables z as a pair composed by a graph G and a set of parameters theta. So G is a directed acyclic graph over the variable z, and we call it the network structure. And theta is a set of CPTs, so these are conditional probability tables for the variable z, and we call it the network parameterization. So we have these two components. One is the graph structure, and the other one are the parameters that specify the strength of the dependencies between the variables. So we're going to use theta x given u to denote the CPT, where we have a variable x and its parents u. So we know that for each node we specify one CPT, and we call this CPT theta x given u. We call the set of variables x and u, so x is the variable, u the parent, a network family. So we know that each node will have a CPT that involves the network family. And we call little theta, little x given little u, as a network parameter. And that specifies the probability of x given u. So in this example here, we have the graph structure. So this is G, and this is the set of parameters that we call the big theta. And for each node, we have a conditional probability table. For instance, for the node B here, we have this conditional probability table that involves the node, the variable B, and the parent that in this case is A. We call BA the network family for the node B, and each entry here has one parameter. It's a conditional probability that we call little theta given little theta of B given little a. When we assign a value for each of the network variables, we have what we call a network instantiation. So we can call it z, and we need to give one value for each variable. So I would say that A is true, B is true, C is false, D is true, and E is false. If we do that, we are specifying the values for each of the conditional probability tables. We say that a certain network parameter is compatible with this instantiation here if it agrees with the common variables. And we haven't seen this definition before. We use this symbol here, the tilde, to specify that it is compatible. So in this case, for this network instantiation Z, we can look at what are the compatible parameters, and we will see that we have A true and B true, so we're going to use this parameter here. We have, for this table, we have B true, C false, and D true, so we have this network parameter here. For A here on the top, A is true, so we have this parameter here. For C and E, we have not C and not E, so we have this parameter here. And for A and C, we have A and not C, so we have this parameter here. So these are the parameters that are compatible with this instantiation here. And this is probably the most important definition of all. we call it the chain rule for the Bayesian networks. So we discussed this before. For each network instantiation, we know that the Bayesian network will assign a single probability value. And it will assign one probability value for each possible variable assignment. So it will be complete and unique at the same time. So we need to know a way to compute that probability. So let's continue with the example that we had before. So we have this network instantiation here, and I want to compute what is the probability for this network instantiation. And the definition says that we should take the parameter that is compatible with the network instantiation and multiply all the parameters. We will have one parameter for each probability table, so we will take each node and multiply the parameters. So for this example that we have little a, little b, not little c, little d, and not little e. We're going to take the compatible parameters. So from variable a, we will take a equal true, so it's going to be 0.6, exactly what we have here. And we will multiply by another compatible parameter that is for variable b, the parameter little b given little a. So it will be this one, that is 0.2. If you look at variable c, we see that we have an instantiation that assigns not c and a. So it's going to be the parameter theta not c given a. And we will find it here. So it's not c and a, it's 0.2. We have another one that is d given b and not c. So we have b, not c, and d. So we have this parameter here, 0.9. And finally, we have not e given not c. So we have this parameter here, right? That is 1. And we multiply this. So we're going to multiply 0.6 with 0.2 with, again, 0.2 here with 0.9 here and 1 here. And the result is 0.0216. So this is the probability assigned to this instantiation here. Of course, we can change the network instantiation. We're going to change the variables, and we can look for each possible combination of variable values, and we can complete and have the complete conditional, the joint, not the condition, but the joint probability distribution. So we can fill in the joint probability distribution with all possible combinations of network values. And that is the most important definition for Bayesian networks. And we know for the joint distribution that it will grow exponentially with the number of variables. So we can say that for the joint distribution, the size of the table will be proportional to, if we assume that the variables have d different values, so it's going to be d elevated to the power of n. So it's going to be exponential in the number of variables. And we can make a similar analysis to with the Bayesian networks. In this case, what we needed to control is the size of the CPTs. And the size of the CPT is dictated by the number of parents that a variable has. So if we look at the largest CPT and it has k parents, so the size of this CPT will be will be of the order of d elevated to k plus 1. It's k plus 1 because we have the k parent plus the node, that the variable that is in the node. So we have to account for this variable too. So in this case, for instance, that we have this CPT here, we have two parents, right? But we have to account also for the variable d. So in total, we have 2 elevated to the power of 3 because we have 2 parents plus the variable d. The good news is that with the factorization of the Bayesian network, the size of the network will be bounded by this quantity here. And it's very simple to understand. What you're thinking is that we consider the largest CPT, and this largest CPT has k parents. So the size of the largest one will be d to the power of k plus 1. And we are thinking about an upper bound, right? So, and we have any of those tables. So it's going to be any times d to the power of k plus 1. And this is an upper bound. And so these are good news because we have this initial situation here for the joint probability distribution where we have an exponential growth in the number of variables. And now we have this expression here for the Bayesian networks where the growth is linear in the number of variables, but is exponential in the number of parents. So in other words, the Bayesian networks will be a compact representation if we keep the number of parents small. And in order to do that, we know that we have to make some assumptions of independence between the variables. And we know that the graph structure will dictate a series of independence assumptions that are known as the Markovian assumptions. So the Markovian assumptions, they have this form here, and they say that a node, a variable x, is independent of all its non-descendants given its parents. So for instance, if we take the variable r, we know that r is independent of all non-descendants. So r has not a single descendant here. So the non-descendants are a and c and b given its parents, and it has just one parent, and that's e. So we have this assumption that is encoded in this graph structure. But that is not the only independence assumptions. There are more. For instance, we have this independence assumption here that's pretty similar to the Markovian assumption, but it's a little simpler. It's just saying that r is independent of a given e. So it's saying that this variable here, r, is independent of a given its parent. So it seems that we can obtain this independence here that is slightly different from this one using some form of some operations. And that's true. So the message is that we can obtain all possible independences that are encoded in this graph by operating over the Markovian assumptions. So it's like thinking that the Markovian assumptions are the basic dependence assumptions, but that they are not the only ones. There are more independence assumptions, but I can obtain all the other independence assumptions by applying a series of operations. So we have several properties that are valid for independences that we call symmetry, decomposition, weak union, and contraction. And using those properties, we can derive all the other possible independences that are encoded in the graph. So we call those properties the graphoid axioms, and we're going to see the definitions for those properties. So what I'm telling you is that we can have the following procedure. So we can design a graph. We can, from the graph, obtain the Markovian assumptions. And using the graphoid axioms, we can derive all the possible independence assumptions that are encoded in this graph. Right? So you have a complete list of all possible independence assumptions. We will see that, okay, we can do that, but it will involve a lot of work. And we will find what I call a computational procedure for doing that. That will be a series of operations that we do over the graph. So instead of operating over the independence assumptions and manipulating them, we will look graphically and derive all those independencies using a different procedure that is more computational and will involve just the graph structure. So let's start looking at what are those properties, and we'll follow with this operation over graphs. The first property is known as symmetry, and it's the simplest of all the properties that I'm going to see. It states that if you have x independent of y given z, I can invert that and say that y is independent of x given z. So we haven't seen this before. When we discussed independency, we saw that it's a property of independency that if A is independent of B, B is also independent of A. So what we can do with that, right? So we have this is a Markovian assumption for variable A. So it says that A is independent of R, that it's the only non-descendant of A given the parents that are B and E. So we can invert that and obtain that R is independent of A given B and E. The second property is also very simple, and it's called decomposition. It states that if we have a variable x that is independent of y and w given z, it means that x is independent of y given z and x is independent of w given z. So it's basically saying that we can decompose, right? If you have a statement like this in which x is independent of a set of variables given another variable, we can decompose this set here into smaller sets. So we can look at one example. So here we have the Markovian assumption for variable r. It says that r is independent of its non-descendants. So the non-descendants are A, C, and B, given its parent, that is A. And we can decompose this set here into smaller sets. So in this case here, we are making 3 decompositions for A, C, and B. So we chose to make the decompositions for subsets of size 1, but we could also state that R is independent of a subset of size 2, like A and C given E, right? So we have more possibilities here. And decomposition is the key property to prove the chain rule for Bayesian networks. And the chain rule for Bayesian networks has this format here. So it says that if you want to compute the probability for an assignment Z, what you have to do is to multiply the conditional probabilities for each node so that we take from each CPT the entry that is compatible with Z. So for instance, if you have this assignment here, it means that we're going to take the probability of E, because E has no parent, so it's going to be just E. The probability of B, because B also has no parent. The probability of R given E, because R has one parent, that is E. The probability of A given its 2 parents, these are E and B, and the probability of C given its only parent A. We know that it's not true for every possible distribution. We are making some independence assumptions here. In order to understand which independence assumptions we are doing, we can use the chain rule. So this here on the bottom is the chain rule, and we know that there are n factorial possible chain rules, so we are choosing one that is very special, that will match in some way our chain rule for the Bayesian networks. So I decompose the joint distribution by choosing first the variable E. That's okay. Now I'm going to choose for the chain rule the variable b. So it's going to be given this first variable here, that's e. I will choose for the third variable r. It's going to be r given the two variables that I had before, there are b and e, and I continue doing that. So I choose for the next one, that's a, given everything that came before, that is e, b, and r, and we have c given everything that came before. So in order to match those two things, we need to make a few independence assumptions. So it's important that those independence assumptions that we are doing are encoded in this graph. So in other words, are encoded into the Markovian assumptions. So, okay, here we have a match, right? So we don't need to worry about this. This we don't have a match. We are saying that B is independent of E, right? And that is true for this assignment, but it's also true for the variables. So I will here write this as variable. So we are saying that B is independent. B is independent of E. So is that true in our network? Well, okay, so B is independent. So what we know is that B is independent. So this is the Markovian assumption. B is independent of every known descendant, there is E and R, given its parents. And B has no parents. So if you look at this, there is no match. So there is no match between this independence assumption here and the Markovian assumption. But we can use the composition and say that B is independent of E, and also B is independent of R. And now we have a match, right? So we have a match between these two guys here. So, okay, that's true. So, okay, we don't have to worry about the second one. And for the third one, we are saying that these two probabilities are equal, P of R given E and P of R given B and E. Well, what assumptions are we doing here? We assume that R is independent of B, that was eliminated, given E. All right, do we have this in our Markovian assumptions? Let's take a look at the variable R. And the variable R, the Markovian assumptions that says that R is independent of its known descendants. There are B, A, and C, given its parent, that's E. So again, I don't have a match between the assumption that is implied by matching this guy here with this guy here, but using the composition, I can show that R is independent of B given E. So I decomposed this guy here into this, and I have a match with this guy here. Okay, that's true. And we can do that for all possible ones. So we continue doing this, and we prove that, at least for this example, this is true. We can work a little bit more and show that it is true for every possible Bayesian network. And the next property is called weak union. So weak union says that if X is independent of Y and W given Z, it means that X is independent of W given Z and Y. So just one example, we can take the Markovian assumptions for variable C. So C is independent of all the non-descendants, the R, E, B, given its parent A. And using a weak assumption, we can move some of the variables that we have here to this side here, as far as we keep A in that place. So we can say that C is independent of, I don't know, R given A, E, B. I find that the weak union is a little less common to use than the decomposition. And there is a mistake here. It should be weak union. I will fix that in the slides later. But weak union seems to be less useful than decomposition, because if we use decomposition, we start with this. So this is using weak union, but we could use decomposition from here and state that C is independent of R given A. So we already know that. So it seems to me that the key information here is the parent A that is blocking the influence of the variables. And this is a way of doing the decomposition. What we are moving the variables from this side here to this side when we know that the key information is the parent for the Bayesian networks. But it's still valid and it's still useful in some situations. And our fourth property is called contraction. In order to illustrate this property, I will use a different graph. So we call this graph a chain for obvious reasons. So we have this sequence of nodes. Frequently, those nodes are considered as a sort of an update of the structure over time. So it's very common to have the node called xt, and t represents time. So x1 should be the first time step, and in the second time step we create a second node and keep updating and growing the model as the time passes. I will not get into details here about this because we will have one lecture just to discuss this kind of graph. And we see that in the simplest form it is called a Markov chain, but we can increment a little bit and we will call it hidden Markov models. So in this graph here, we have these properties, right? So we have this x3 node is independent of x1 given x2, that it is his parent. So we have x3 independent of x1 given x2. Similarly, we can say that x4 is independent of x1 and x2 given its parent that is x3. And we can manipulate this a little bit, so we can use the contraction property. So let's take these independents here and move x2 to this side. So we can use the weak union in order to move things from one side of the bar to the other side of the bar. In this case, we will have x4 independent of x1 given x3 and x2. So yeah, I get this from weak union. And we can invert x4 and x1 using symmetry. So we can get x1 independent of x4 given x3 and x2 by symmetry property. And we can also invert this one here and have x1 independent of x3 given x2, and also use symmetry from the first independence. So if we look at these two here and we try to map to the contraction property, you're going to see that this will be x. So this is x. X3 is going to be y. So we have y here and y here. We have x4, that's going to be our w, and x2 is going to be z. Alright, so we can work it, and using contraction get x1 is independent of x3 and x4 given x2. So it's saying that this node x1 is independent of these two here, x3 and x4, given this middle node. That's something that we didn't have when we started with the Markovian assumptions. So, okay, we have one more property. And this property is called an intersection. So this property is a little bit special because it is restricted to what we call strictly positive distributions. So these are distributions where we don't find zero probabilities. And because the distribution, the probability in the distribution must sum to 1, it also means that we don't have 1 probabilities. So we will not have those deterministic probabilities in this case. So it will hold for every probability distribution, but to those that are deterministic. So I will just show to you one example where the intersection property does not hold because we have one of these deterministic distributions, and that case can be easily illustrated when we have a digital circuit, because in a digital circuit we have these deterministic distributions. So in this example here, we can say that this is the output. So the output E is going to be independent of A, that is the input, if I know C. As I can determine C from A and A from C, if I have just one piece of information, it will make the other piece of information irrelevant to knowing the output. At the same time, we can invert that and say that E, that is the output, is independent of C, that is this intermediate signal here, given A. Again, because knowing one, I will know the other one, and I can figure out what's going to be the output. And if we take these two dependencies here, we can analyze here. So in the simplest version of intersection, we can consider Z as an empty set of a variable. So I will remove Z from here, remove here Z from here, and remove Z from here. It's going to be a little simpler. So we can see that E is going to be X, A is going to be Y, and C, W. And basically what we have at the end is that E is independent of A and C. And that is clearly not true, right? I cannot say that E is independent from this side of the circuit, right? So, so clearly the intersection property took us to an incorrect result, but it only happened because we are working with a circuit that has deterministic probabilities. So these are the properties, and again, the good thing of thinking about those properties is the fact that we can start with the Markovian assumptions and use those properties to convert the Markovian assumptions in every possible independence that holds for a graph. So that's very interesting, but as we haven't seen, it is a lot of work involved, so it's not easy to do. So we need a simplest way of doing that, and the simplest way of doing that is using an algorithm that's called d-separation. And the d-separation is easy to do, but because it is a graphical algorithm. So we just look at the graph and we can figure out all possible independence assumptions that hold for that graph. And that is what you're going to see in the next video. So I'm going to make a pause now and continue in the next video with the d-separation algorithm.